what I want to talk to you about today has to do with the study of isomorphisms. And it's fair to say that in mathematics, we typically study objects up to isomorphism. And let me get the definition straight so everyone knows it, but still doesn't hurt to repeat it. I'll focus on graphs on this talk, and in particular on finite graphs for most of the talk. So if we have two graphs, they are isomorphic if there is a function h from the vertex of the first to the vertex of the second, which is a bijection. And for all pairs of nodes in the first graph, there is an edge between them, if and only if there is an edge between their images in the second graph. And of course, this can be generalized to the notion of isomorphism between relational structures. Again, our focus here would be on finite graphs and on finite relational structures in general. And that gives rise to a fundamental algorithmic problem. And the problem is, given two finite graphs, are they isomorphic? And this problem has been around for decades. And to this date, it remains open in the sense that we don't understand the exact computational complexity of the graph isomorphism problem. The next slide will provide a summary of what we know about this problem. On the face of its definition, the graph isomorphism problem is in NP because you can guess the bijection and verify that it is an isomorphism. It is not known, however, to be solvable in polynomial time. And there is a resulting structural complexity theory that suggests it is unlikely to be NP-complete, because if it were NP-complete, then the polynomial hierarchy would collapse. And since we believe that the polynomial hierarchy does not collapse, this makes it unlikely to be NP-complete. This is a conditional result. In terms of upper bound, the best well-known algorithm is a quasi-polynomial time algorithm, which means it's 2 to the big O of log n to the c for some fixed positive c. And that's a celebrated result by Laszlo Babai at the University of Chicago. On the other hand, in the process of trying to understand the complexity of the graph isomorphism problem, numerous restricted classes of graphs have been identified on which the problem is solvable in polynomial time. More than 50 years ago, Hopcroft and Wong proved this for planar graphs. Then, using algebraic methods, Jean Lux in 1982 proved it for graphs of bounded degree, Bodlander in 1990 for graphs of bounded tree width, and the list is long. I'm not going to attempt to summarize everything other than convey the idea that there is a lot of work around the problem, but the problem is still not understood. The complexity of the isomorphism problem remains one of the open mysteries of theoretical computer science. So much so that a long time ago, Reed and Cornet wrote a paper titled The Graph Isomorphism Disease. And the idea was that when you start thinking about this problem, you get infected by the appeal of the problem, and you get this disease, and you only think about this problem. Now, I said in mathematics, we typically study objects under isomorphism, but we also study objects up to some other equivalence relation. For instance, in topology, objects are studied up to homeomorphism, in differential geometry up to diffeomorphism, in first-order logic up to logical equivalence. Now, on finite structures, logical equivalence coincides with isomorphism, but that's not true for infinite structures. So we have all these other equivalence relations on which we can focus and study different areas of mathematics. Here, we will focus on equivalence relations on finite graphs that arise from homomorphisms. And so I need now to remind you of what a homomorphism is. In some sense, a homomorphism is a relaxation of the notion of isomorphism. If I have two graphs, a homomorphism from the first to the second is a function from the nodes of the first to the nodes of the second, so that if there is an edge in the graph on the left, then the image of the edge under this function is an edge in the second graph edge. And we will use the notation G arrow H to mean that there is a homomorphism from G to H. in other words, the notion of homomorphism relaxes the notion of isomorphism two ways. You drop the bijection, you only require a function, and then you relax the preservation of the edges to be only from left to right, not from right to left. Now, let's look at some examples that will keep us busy. I'll come back to these examples from time to time. Suppose I have a graph, and let K3 be the triangle graph, the clique with three elements. Then it is easy to verify that there is a homomorphism from the triangle graph to the arbitrary graph G if and only if G contains a triangle. But if you switch sides and you ask, what does it mean to say I have a homomorphism from G to K3 to the triangle? This happens if and only if G is three-colorable. This requires a moment's reflection, but it's a very well-known fact and typically an exercise in books. So this gives you some sense of homomorphisms. And here is another example. On the left, we have one of the most studied graphs in graph theory, Peterson's graph. And on the right, we have the triangle. There is a homomorphism from the Peterson graph to the triangle. And in fact, I have indicated the blue edges map to the blue edge of the triangle, the red edges to the red edge of the triangle, and the green edges to the green edge of the triangle. This simply is the fact that the Peterson's graph is three-colorable. On the other hand, Peterson's graph is triangle-free. There is no triangle there. Therefore, there is no homomorphism from the triangle to Peterson's graph. So that's the notion of homomorphism between graphs. And now we have another notion that will play an important role in our discussion, and this is the notion of homomorphic equivalence. Two graphs are homomorphically equivalent if there is a homomorphism from G to H and a homomorphism from H to G. So we have homomorphisms going both ways. Examples, if I have two graphs that are two colorable and they contain at least one edge, then they are homomorphically equivalent because you can map each of them to an edge of the other. In particular, if I have a cycle of length 4 and a cycle of length 6, they are homomorphically equivalent. They are two colorable and each contains at least one edge. Here is another example, going back to the Peterson graph. If we take the Peterson graph and we take the disjoint union with a triangle, then of course we still have a homomorphism from left to right, but now we also have a homomorphism from right to left because we map the triangle to the disjoint copy of the triangle. So these two graphs are homomorphically equivalent. And guess what? Homomorphism equivalence is an equivalence relation that is coarser than isomorphism. As we saw before, this previous example shows that these two graphs are homomorphically equivalent without being isomorphic. So this is an equivalence relation coarser than isomorphism. And we understand very well the computational complexity of homomorphic equivalence. The question given to graphs, are they homomorphically equivalent? That's an NP-complete problem. Obviously, it's in NP, easy reduction from three-colorability. The graph is three-colorable if and only if when I take the graph with a disjoint union with the triangle, it's homomorphically equivalent to the triangle. So we understand the complexity of homomorphism equivalence. Now, this is all background. And now I'm coming to the first notion that appears in the title of the talk. And this is the notion of homomorphism counts. So this is very important notation. If I have two graphs, by lowercase hom, HOM, GH, we mean the number of homomorphisms from G to H. So now we're going to count the homomorphisms from one graph to another. Let's get some feeling about this quantity. Let's go back to an arbitrary graph and to the triangle graph. The number of homomorphisms from the triangle graph to G is the number of triangles in G. On the other hand, the number of homomorphisms from G to the triangle is the number of three colorings. And that's another easy to verify fact. So that gives you a sense about this notion of homomorphism count. And in fact, this is so important that I want to give you two different interpretations. one coming from constraint satisfaction and one coming from databases. Fix your favorite graph H. Every graph H gives rise to a decision problem, which is known as the constraint satisfaction problem. And we will denote this by CSPH for constraint satisfaction problem determined by H. The input is a graph G. And the question is there a homomorphism from G to H? This way, the number of homomorphisms from G to H is the number of solutions to the CSP problem arising from H. Now I'm going to look at the same quantity, but in a different perspective, and we'll give a different interpretation of this quantity. Now, instead of fixing the graph H, fix a graph G. Every graph G gives rise to what in databases we call the canonical conjunctive query associated with a graph. This is simply what in logic is often called the positive atomic diagram of a structure. This simply is an existential positive sentence that says there are so many nodes, and then you describe all the edges between these nodes. You don't say anything about absence of edges, but you have a complete listing of possible edges on the variables x, y, z, w, as many as the number of nodes in the graph. So for example, if I take as G to be the triangle graph, then the conjunctive query associated with it says there are 3 nodes, and there is an edge from X to Y, there is an edge from Y to Z, and there is an edge from Z to X. Now with this perspective, the same quantity, but now sort of looking at it from the point of view of G, the homomorphisms GH, the number of homomorphisms from G to H, is the number of satisfying assignments of this canonical conjunctive query when H is given as input. And this is important in databases because it's exactly the bug semantics of SQL. If in SQL you write this query and E is a relation that encodes a graph in the database, that will give you, that's what the SQL will return, will be the number of satisfying assignments of QG on input H. So if you have these 2 different perspectives, the same quantity looked one time from the point of view of constraint satisfaction, the other time from the point of view of conjunctive queries and databases. Okay, we're still defining notions. We want to, before we come to the discussion of the first important result, we want to visualize these homomorphism counts. Take a list. This calligraphic G is the class of all graphs where you take one member from every isomorphic class. So this is a list of all graphs, finite graphs, always up to isomorphism. And now make an infinite matrix where on the rows and the columns, you list these graphs. And in every cell, you have the number of homomorphisms from one graph to the other. So in the second row and the first column, you have the number of homomorphisms from G2 to G1. So this is a way to visualize the homomorphism counts. And now we are going to associate with the graph the left profile and the right profile. What is the left profile? Go back to this table that we saw before. And for the left profile, go to the column that corresponds to your graph G in the listing that you have. And now travel down this column. Go over all the rows. So you have home G1G, home G2G, at some point you have home GG, etc. This vector, the column vector, is called the left profile of G. In other words, it is the vector of all homomorphism counts from some graph to G. You can play the same game by going on the rows. If I fix a row G, and I start traveling along the columns, I now see the homomorphisms from G to G1, from G to G2, from G to G, etc. This is called the right profile. So in the right profile, the fixed graph is on the left, and we let the other, we're looking at homomorphisms, two other graphs. So we have the left profile and we have the right profile. Now you should say, wait a moment, you started with isomorphism. Now you've gone to homomorphisms. Now you tell us about left profiles. What is it all about? Well, what it's all about is Lovas's theorem from 1967. That's Laszlo Lovas. He was at the time 18 or 19 years old. It's one of his first papers. He proved that for all graphs G and H are isomorphic if and only if they have the same left profile. What he says is that in the table we saw before, because we have taken one member from every equivalence class, no two columns are identical. That's what he says. If we had listed all graphs, including elements from the same equivalence class, this would say that two graphs are isomorphic if and only if they have the same columns, the same left profile. So this says G and H are isomorphic if and only if they have the same left profile. No two columns are equal. That's 1967. The proof is not very difficult. It's an analysis of homomorphisms as the composition of a subjective homomorphism and an isomorphism. There is a dual to this theorem, and that came in databases in a very different context. And even when you see it there, it's stated in a very different way. And this is Chowdhury and Vardy, 1993. But apparently, Lovas was aware of this, that for all graphs G and H are isomorphic if and only if they have the same right profile, which means in the table that all the rows are different because we have taken one member from every equivalence class. So what is nice about these results is that they relate the notion of isomorphism to the notion of homomorphism count. In some sense, this tells you that the left and the right profiles of a graph are invariant of the graph for isomorphism, except that they are infinite invariant. They are infinite objects. They are not finite vectors. They are infinite vectors. Any questions so far? Okay. All right. So as I just said, the left profile of a graph can be viewed as an infinite dimensional graph embedding vector that describes G up to isomorphism. That's the essence of Lovas's theorem. Similarly, for the right profile of a graph. Now, what the question is, what can we say if instead of taking the entire infinite vector, we take a subvector of it? In other words, what happens if we eliminate some rows for the left profile or eliminate some columns for the left profile or eliminate some columns for the right profile? Well, so now we are looking at an arbitrary class of graphs, not a class of 4 graphs, just a subclass of the class of graphs. And then the left profile of G restricted to the class is simply the vector hom calligraphic Fg, hom F1G, hom F2G, etc., etc. In other words, here you keep only the rows arising from graphs in your class F. And dually, you can do the same thing going from the right. So the right profile of G restricted to a class is the vector hom GF, hom GF1, hom GF2, etc., etc. This means on our two-dimensional table, you only keep the columns that arise from graphs in F. Good. In turn, now, every class of graphs gives rise to two equivalence relations. Fix a class of graphs. The left equivalence relation says two graphs are equivalent if they have the same left profile restricted to F. The second says two graphs are equivalent if they have the same right profile restricted to F. So this is the most fundamental notion in this talk. We have, again, fix a class of graphs, and we count homomorphism from every member to this class to some other fixed graph. And that gives us the left profile. And now this induces an equivalence relation. Two graphs are equivalent with respect to the class on the left if they have the same left profile, and two graphs equivalent if they have the same right profile. These equivalence relations are clearly relaxations of isomorphism. They are coarser than isomorphism by Lobach's theorem. So the question is, which equivalence relations on graphs are of this form? Left profile or right profile? And once you ask this question, you have a notion of expressive power. What are these equivalent? What equivalence relations can be realized this way? Are there equivalence relations that can be realized as right profiles, but not as left profiles? So this gives rise to a notion of expressive power, and that explains now half of the title of the talk. Homomorphism counts expressive power. That's what we mean by expressive power. What are the equivalence relations that you can capture this way? We don't understand this very well. I just want to give you a sense of what has been accomplished so far. To give you the first important result, which was obtained in 2010 by Zdenek Dvorak, I need to go and say something about logic. It's about time, after all, right? We have said very little about logic so far. And now we want to focus on counting logics with finitely many variables. If I have a positive integer, f of k is first order logic where you have at most k distinct variables. So now we're thinking of number of variables as a resource, and we control this resource. Of course, each of these k distinct variables we can use many, many times. We don't put a bound on how many occurrences a variable has in a sentence, but when we look at these sentences, we require that they have at most k distinct variables. That's a very well-studied logic in finite model theory. There is a pebble game that captures it and things like that. This is a different talk. Now we want to take this logic and add counting quantifiers. So f of k plus counting quantifiers gives rise to the logic ck. And what is a counting quantifier? We throw in all the quantifiers exist, I, y, phi of y, that says there are at least I nodes for which phi of y holds. So for example, the property G7 regular, which means every node has exactly 7 neighbors, is definable in C2 with only 2 variables and counting quantifiers. Because you say for every x, there are 7 y's that are neighbors of x, and it is not the case there are 8 y's that are neighbors of x. So in C2, we can express 7 regular, actually any k regular graph can be expressed this way. There is a very important theorem by Tsai-Führer-Immermann in 1992 in a beautiful paper, one of the gems of finite model theory, which among other things, this is not even the main result, but it's an important result. It says that for every 2 graphs, the following are equivalent. The graphs cannot be distinguished by a sentence of ck. They satisfy the same sentences of first order logic with k variables and counting quantifiers. This happens if and only if they cannot be distinguished by an algorithm introduced in the late 60s by Weisfeiler and Lehmann, which is known as the k-1 dimensional Weisfeiler-Lehmann algorithm. I'm not going to describe this algorithm. This is again the topic of another talk, but it is an important heuristic for isomorphism. It is an algorithm that tries to solve that 2 graphs are isomorphic, and if the algorithm fails, the graphs are not isomorphic. But if the algorithm stops and reports yes, they may or they may not be isomorphic. And it was not clear exactly what this algorithm was capturing, and Tsai-Führer-Immermann pinpointed it. They said what really this captures is not isomorphism, but it is indistinguishability in the counting logic with k variables. And by the way, this algorithm runs in polynomial time. So what you get as a consequence of the Tsai-Führer-Immermann result is the fact that indistinguishability in counting logic with k variables for every fixed k is in polynomial time. Okay, now we have all the background. to state this beautiful result by Dvorak in 2010, who saw that two graphs satisfy the same CK sentences if they have the same profile with respect to the class of all graphs of tree width less than k. I think this is a very beautiful result because it makes a totally unexpected connection between counting logic or by Zephyr-Rimmermann, Weisweiler-Lehmann algorithm and left profiles restricted to the class of all graphs of tree width less than k. Now, I'm not going to define what tree width is. I presume most of you know, but the tree width of a graph is a positive integer that in some sense quantifies how far apart from being a tree the graph is. So every tree has tree width 1, cycles have tree width 2, cliques have high tree width, the clique with n nodes has tree width n minus 1. It's a notion that has played a major role in the study of graph minors and the Robertson-Seymour celebrated theorem. So Dvorak's theorem says that we can capture the notion of indistinguishability in the counting logic with k variables using left profiles. Having the left profile with respect to the class of graphs of tree width less than k means exactly that you cannot distinguish them in the counting logic with k variables. That result, in some sense, provided the impetus for many other results that try to identify equivalence relations on graphs as arising from the left profile restricted to some interesting class. Here is one of the many corollaries of this result combined with what I told you before. I give you two graphs and I tell you, do they have the same left profile with respect to the class of graphs of bounded tree width less than k? This problem is in polynomial time. Why? By Dvorak, it is equivalent to indistinguishability in counting logic with k variables. By Zephyr-Rimmermann, this is what the Weisweiler-Lehmann algorithm gives you. So you have a p-time algorithm for deciding if two graphs have the same profile with respect to the class of graphs of tree width less than k. Imagine if you had to test this directly. You have to test all graphs of bounded tree width. So that's one of the many nice consequences. Let me give you another result. And for this, another result of this flavor in this spirit. And for this, let me bring a notion from graph theory called cospectrality. Two graphs are cospectral if their adjacent matrices have the same spectrum. And by spectrum, we mean the same multiset of eigenvalues. So you count the multiplicities of eigenvalues. The two graphs you see on this diagram, on this picture, are the smallest graphs that are cospectral without being isomorphic. One is the cycle with 4 elements, the joint union with a single isolated node, and the other is the star with 5 nodes. You can show that these two graphs have the same spectrum, and the spectrum is the eigenvalues is -2, 2, and 0 with multiplicity 3. So that's an example of cospectrality, and there is a nice result here by Dell and Groy that says two graphs are cospectral if and only if they have the same left profile with respect to the class of cycles. So cycles, you restrict the homomorphism count to cycles, you capture cospectrality. So here is another fundamental equivalence relation on graphs, cospectrality, which can be captured by homomorphism, by left profiles. So what have we seen so far? We have seen that the restricted left profiles can capture interesting relaxations of isomorphism, and we saw two such examples, CK equivalence and cospectrality. There are many more. I will discuss one more later on. When I learned about these results, I was working with my student who has now graduated, Wei-Lin Wu at UC Santa Cruz. And coming from the databases, I was more aware of the right profile in the Tsaouturi-Vardi theorem. So we started asking the question, what happens with the right profiles? Can we obtain these results using right profiles? In particular, can CK equivalence and cospectrality be captured by restricted right profiles? In other words, can you do from the right what you can do from the left? Or is there a superiority of the left over the right or the other way around? And Albert Acherias joined us in this project, and we had a paper in Leaks 2021 on the expressive power of homomorphism counts. And let me again raise the question using a picture at this time. We have the class of all graphs. We have the class of graphs of tree width less than k and the class of all cycles. As when you take the class of all graphs, then the left and the right profile give you the same equivalence relation, isomorphism. When you have the class of bounded tree width, you get CK equivalence on the left. What happens to the right? When you have cospectrality, you get you can capture it with the left profile restricted to cycles. Are there classes that you can put on the right that can CK equivalence and cospectrality be captured by restricted right profiles? And the answer will turn out to be no, turns out to be no. And our main result implies that these two equivalence relations and many, many more others cannot be captured by a restricted right profile. So here is the theorem, the main theorem from our Leaks 2021 paper. Suppose I have an equivalence relation of graphs that is sandwiched between C1 equivalence, counting logic with one variable. All you can do is count the number of nodes you have in the graph, and coarser than CK equivalence for some k bigger or equal than 2. So this is sandwiched between C1 equivalence and some C25 equivalence, in general CK equivalence from some k. For every such equivalence relation, there is no class F, so that you can capture it by restricting the right profile to this class of graphs. So the right profiles are unable to capture any such class. And in particular, they cannot capture CK equivalence, and we will see why they cannot capture cospectrality. So this reveals a limitation of what you can do with restricted right profiles. Before, with the left profiles, you could capture CK equivalence and cospectrality. This you cannot do from the right. Okay, so this is the result, and I want to give you a sense of how this result is proved. It's proved by contradiction. So you assume that there is a class F, so that for all graph G and H, G is equivalent to H if and only if G and H have the same right profile restricted to F. And remember, this equivalence relation is finer than C1 equivalence and coarser than CK equivalence from some fixed k. There are two cases to consider. The first case is very trivial. First case, all graphs in the disputative class F are two colorable. Well, then pretty much you are done, because K3 and K4, the triangle and the clique with 4 elements, you can separate with formula in counting logic with one variable. You say how many nodes there are. Therefore, because our equivalence relation is finer than C1 equivalence, they are separated. They are not equivalent with logic. On the other hand, neither K3 nor K4 are two colorable. Therefore, their homomorphisms to every member of the class, the number of homomorphisms to every member of this class F is 0, because we assume that the class has only two colorable graphs. So they have the same right profile, and therefore they have to be equivalent. So that's the contradiction. That's, I said, this is quite trivial. The interesting case is when the class F contains at least one non-two colorable graph H star. So now we have a class that presumably captures this equivalence relation in terms of the restricted right profile, and this class contains at least one non-two colorable graph. Let's fix this graph H star. Now we need to bring into the picture a another very nice theorem from constraint satisfaction by Helen Nesetril in 1990. This is dichotomy theorem. They said if the graph is too colorable, then the constraint satisfaction problem with respect to H is in polynomial time. Remember, the constraint satisfaction problem is the question, given a graph, is there a homomorphism to H? And if it is not too colorable, it is NP complete. All the work there goes in the second part, because if it is too colorable, then basically the algorithm for two colorability, the polynomial time algorithm for two colorability. The interesting case is when the graph is not too colorable, and then they did a lot of hard combinatorics to series of reductions to prove that the constraint satisfaction problem is NP complete. With this result in the background, and using some other results from the study of constraint satisfaction that took place in the 90s and early 2000s, we were able to prove a definable dichotomy theorem. A dichotomy theorem for constraint satisfaction on graphs, which is along the lines of definability in logic. And the theorem says if H is too colorable, then the constraint satisfaction problem not only is in p-time, it's actually definable in the complement of data log. And this was a non. Non-to colorability was known to be expressible in data log. Data log is existential positive inductive definitions from the logicians, or conjunctive queries plus recursion if you come from databases. The new thing here is that if the graph is not too colorable, then the constraint satisfaction is not definable not only in the counting logic, but even in the counting logic with infinitary conjunctions and conjunctions. So CM infinity omega is the infinitary logic, allows arbitrary conjunction disjunctions, but counting quantifiers and at most M variables. So this is where we had to do some work using other results from constraint satisfaction. By the way, I should say that this suppose tomorrow someone proves that P equals NP. Then the dichotomy theorem of Helen Nesetril goes away. Then it's trivial. On the other hand, this definable dichotomy theorem is an absolute result. It's not conditioned to be a dichotomy on assuming that P is different from NP. It's an absolute result. Okay. Now, once we have this result, we can finish the proof. We have assumed that the class F contains a graph which is not too colorable. Okay, so we grab this graph which is not too colorable. By the definable dichotomy theorem, it is not, the CSP problem with respect to this graph is not definable with K quantifier, with K variables and counting quantifiers. This means there are two graphs, so that one is a yes answer to the constraint satisfaction problem with respect to H star. The other is a no answer, but they're indistinguishable in counting logic with K variables. Since G0 is in CSP of H star, it means that there is a homomorphism. So the number of homomorphisms is positive. Since G0 is CK equivalent to G1, and our equivalence relation is coarser than K equivalence, it implies that the graphs are equivalent. Therefore, they have the same homomorphism account. But that's a contradiction because H star G1 is not in CSP of H star, so the homomorphism account is 0. So you get the contradiction in a straightforward way once you have obtained the definable dichotomy theorem. That's all I wanted to say, just to give you a sense of the techniques involved to prove this result. So let me restate it again. The main theorem says that if I have an equivalence relation which is sandwiched between C1 equivalence and CK equivalence, then there is no class of graphs, so that this equivalence relation arises from the equivalence relation determined by the right profile restricted to the class F. Immediate corollary, there is no class of graphs, so that the right profile restricted to this class captures CK equivalence. It also gives you as a corollary that there is no class of graphs, so that the right profile restricted to the class captures cospectrality, and the reason is that cospectrality is finer than C1 equivalence and coarser than C3 equivalence. So it's sandwiched between 1 and 3 in the counting logic. So you get it from the main result. So what we have seen so far, in some sense, is that there are things you can do from the left that you cannot do from the right. Well, it turns out there are things that you can do from the right that you cannot do from the left. And this is brings the notion of chromatic equivalence. Two graphs are chromatically equivalent if they have the same number of n colorings for every n bigger or equal than 1. This is a very old notion, was introduced by George David Birkhoff in 1912 when he was trying to settle the four-color theorem, and then was studied extensively. There is also a chromatic polynomial that gives you this same number of the number of n colorings of a graph. So it's a very well-studied notion, especially in algebraic graph theory. Now, chromatic equivalence is very easily captured by the right profile restricted to the class of all cliques, all complete graphs, because homomorphisms to cliques are number of colorings, number of n colorings. So for all graphs G and H, we have that two graphs are chromatically equivalent if the number of homomorphisms from G to Kn is the number of homomorphisms from H to Kn for every clique, for every Kn in the class of all cliques. It is relatively straightforward to prove, much easier proof than the one before, that there is no class of graphs, so that the left profile restricted to F captures chromatic equivalence. So this is an indication that there are things you can do from the right, but are not things you can do from the left. So there is no superiority of left over the right here. And there are things we cannot do neither from the left nor from the right. Using basically Pebble games and Verenfoyd-Fréchet games, you can prove that first FOK equivalence. FOK equivalence is satisfy the same first order sentences with at most k variables. QD equivalence, QDK equivalence means satisfy the same first order sentences of quantified depth at most k. You cannot express them neither from the left nor from the right. So the picture is quite complex. There are things you can do from both the left and right, like isomorphism. There are things you can do from the right, but not from the left, and the other way around, and things you cannot do either side. The study of homomorphism, the study of restricted left profiles has advanced significantly. I want to mention a very important result by Laura Manciska and David Robertson. There is a notion of quantum isomorphism. Again, I won't define the notion. You can cast isomorphism as a game, and then there is a quantum version of this game with quantum strategies. So it's a relaxation of isomorphism. Let me put it this way, that it uses concepts of quantum mechanics. Manciska and Robertson proved that two graphs are quantum isomorphic if and only if they have the same left profile restricted to the class of all planar graphs. That's one of the most fundamental class of graphs, planar graphs. Having the same left profile restricted to planar graphs is the same as being quantum isomorphic. One of the corollaries of this result, combined with other results, is that telling if two graphs have the same left profile on the class with respect to the class of planar graphs is undecidable. It's undecidable. Why is that? Because there was another result by Atserias, Manciska, Robertson, Samal, Severini, and Varvitsiotis from 2019 that quantum isomorphism is undecidable. So quantum isomorphism is undecidable. Quantum isomorphism is same left profile with respect to planar graphs. Therefore, deciding if two graphs have the same left profile restricted to planar graphs is an undecidable problem. So you see, when you restrict these classes of graphs, when you take the restricted homomorphic, the left profile or right profile, the equivalence relations can be even undecidable. Can be in polynomial time, as we saw before, in the case of graphs of bounded tree width, all the way to undecidable. So a very complex picture. Okay, in the remaining 10 minutes that I have or so, let me mention one more result, though, before I do this. And this is a result by Tim Seppelt. Seppelt is just got his PhD last November at RWTH in Aachen, a student of Martin Grohe. He proved the following interesting result. That if a logic is self-complementary, I'll explain what it means, then equivalence in this logic is captured by the restriction of the left profile to some class, if and only if it's captured by the restriction of the left profile to some minor closed class F prime. So some class closed under minors. And self-complementarity means that for every sentence in the class, there is some other sentence, psi bar, so that the graph satisfies psi if and only if the complement of the graph satisfies psi bar. All the standard logics we consider FO, FOK, quantifier depth K, CK, all these have this self-complementarity property. And this result, you can think of it as a structural meta theorem. It tells you that you can only use classes that are minor closed to capture equivalences arising from logics as long as the logic is self-complementary. It has a whole bunch of consequences that I don't have time to talk about this. I want to spend the rest of the time discussing the other part of the title, which is query algorithms. So far, in some sense, we have looked at restrictions of the left and right profile that are obtained by infinite class of graphs. But what if you consider finite class of graphs? And this work was done a long time ago. Similar work was done by Bieletsky and Van de Bussche in a database conference in 1993. It passed unnoticed. A variation of this came up in the work of Chen, Flum, Liu, and Zhang in 2022. So they introduced a framework for testing membership in a class of structures using finitely many homomorphism counts. So let's take the semi-ring of the natural numbers, which is also known as the bug semi-ring. And we say that a class of structures now admits a left query algorithm if there are structures F1, Fk for some k, and a subset of n to the k, so that a graph belongs to the class if and only if the finite vector of homomorphism counts from F1 to G, F2 to G, Fk to G belongs to the set X. So you try to decide, it's like property testing. You want to test whether you belong to a class, think of it as a property of graphs, but all you are allowed to ask is questions about homomorphism counts coming from a finite set of structures. And you want this to be in the set X. So the left query algorithm is determined by the finite class of structures and the set X. So that's the definition again. They introduced the notion and they proved some interesting results. For instance, they proved that every class of graphs definable by a Boolean combination of universal first-order sentences admits a left query algorithm over the natural numbers. So you can do from the left Boolean combinations of universal sentences. From the right, you cannot do that because the class of triangle-free graphs does not admit the right query algorithm. I didn't define what the right query algorithm is, the similar notion, but from the right. So they saw this difference between left and right at the level of query algorithms over the natural numbers. So in joint work with Balder Tenkate, Victor Dalmau, and my student Wei Lin Wu, we studied last year query algorithms over the Boolean semi-ring and compare them to query algorithms over the semi-ring of the natural numbers, which was the Chen Flum et al. Setting. What do I mean by homomorphic counts over the Boolean semiring, it's just 1 or 0. It's just the sign of the homomorphism count. Hom B Fg is 1 if there is a homomorphism from F to G, and 0 otherwise. So you just keep here a binary vector, a Boolean vector. And this was in a paper that appeared in the International Conference in Database Theory last year. When do homomorphism accounts help in query algorithms? So let me give you formally the definition. We say that a class of structures admits a left query algorithm over the Boolean semiring if there is a K and there are K structures and the set X subset to 0, 1 to the K, now that's a finite set, such that for every structure G, G belongs to the class if and only if this binary vector of the indicators, there is a homomorphism, there is no homomorphism, etc., belongs to X. What's the difference between this and N? Well, in the end, you have the actual count, and the set is a subset of N to the K, just to remind you and contrast the two definitions. The first thing we did was to completely characterize when a class of structures admits a left query algorithm over B. This has 3 parts. It says this happens if and only if the class is definable by a Boolean combination of conjunctive queries, if and only if the class is first order definable and closed under homomorphic equivalence. 1 implies 2 implies 3 is very straightforward. 3 implies 1 is easy, it's not very difficult if you use heavy machinery. And the heavy machinery comes from tools that Ben Rosman developed in 2005 when he proved the preservation under homomorphism theorems in the finite. It doesn't follow from his theorem that his theorem says that a first order sentence is preserved under homomorphisms on finite structures if and only if it is equivalent to an existential positive sentence. That doesn't follow from the theorem, but he developed some technology, and if we take some parts of his technology, we can use them to prove the direction 3 implies 1, that if it's first order definable and closed under homomorphic equivalence, then it admits a left query algorithm. In particular, what this tells you, if you start with a class which is closed under homomorphic equivalence, then the class admits a left query algorithm over the Boolean semiring if and only if it's first order defined. There are many natural classes of structures closed under homomorphic equivalence. For example, all the constraint satisfaction problems, pretty much from the definition, it follows they are closed under homomorphic equivalence. So this characterizes which CSPs, which constraint satisfaction problems are first order defined. Admit left query algorithms, namely precisely the ones that are first order definable. Another example is you take a graph and you take its homomorphic equivalence class. That's first order definable if and only if it admits a left query algorithm, because obviously the class is closed under homomorphic equivalence. So this completely characterizes which classes admit a left query algorithm over the Boolean semiring. Now, if you admit a left query algorithm over the Boolean semiring, you admit the left query algorithm over the natural numbers. The converse is not true, because we can take, for instance, the class of graphs with at least 7 edges. This, you cannot do it with a left query algorithm over the Boolean, because this class is not closed under homomorphic equivalence. And as we saw before, everything that admits a left query algorithm over the Boolean semiring is closed under homomorphic equivalence. But that's an unfair comparison, because as I said, if you admit a left query algorithm over B, then C is closed under homomorphic equivalence. So there is at least 7 edges. It was not fair. You lose from the beginning, so to speak. So the real question is there a class of structures closed under homomorphic equivalence that admits a left query algorithm over the natural numbers, but it doesn't? For instance, is there a structure H where the constraint satisfaction problem admits a left query algorithm over the natural numbers, but it's not first order definable? In plain words, is counting more powerful than existence as regards homomorphic equivalence classes? And we tried for a long time to find such examples, and we failed, and then we realized there is a good reason. There is no difference. So this was the surprise and the main result of the paper, that if you have a class of structures that is closed under homomorphic equivalence, then the following are equivalent. The class admits a left query algorithm over the natural numbers, if and only if it admits a left query algorithm using the same structures but changing the set to some appropriate set over 0, 1 to the k. I don't have time to go to the, I want to leave some time for discussion and questions if there are any. I will just say that the interesting direction is only 1 implies 2, because as I said, if you admit over the Boolean, you admit over the natural numbers. The idea is to write this X as the joint union of some simple sets, and then show that if you are closed under homomorphic equivalence and admit a left query algorithm and the set is a simple set, what we call a basic set, then it's definable as a Boolean combination of conjunctive queries. And so that requires some work, and that uses some results from polynomial interpolation for interpolation about multivariate integer polynomials. I'm not going to elaborate on this. The important thing to take from this discussion is that as regards classes of structures that are closed under homomorphic equivalence, then having a left query algorithm over the natural numbers gives you no advantage. You also have a left query algorithm over the Booleans. And these are the results I wanted to discuss. What are the conclusions here? I hope to have made the case that homomorphism accounts are a meeting point of several different areas. Finite model theory we saw through the counting logics, through the work on constraint satisfaction. Graph theory, certainly a lot of results from structural graph theory come into place, and computational complexity, because we saw when we took these restricted classes, we can go from polynomial time all the way to undecidability. It's an area that is catching some traction, and several people from different groups are working on it right now. For me, the most interesting thing would be to try to establish additional meta-theorems. The result of Tim Seppelt that I mentioned before, and in some sense the result from the LIXT 2021 paper, you can think of it as a structural meta-theorem because it doesn't focus on a particular equivalence relation or on a particular class of structures, but it talks about the whole family of equivalence relations or about whole arbitrary collections of structures. There must be additional meta-theorems, and it will be very interesting to investigate them both from the left and from the right. The result I showed you that counting doesn't buy you anything over existence was about left query algorithms. We don't know what happens over right query algorithms. And last but not least, we focused here on homomorphism accounts on the natural numbers and over the Boolean semiring. But there is another area work now in database theory that studies databases with annotations over arbitrary positive semirings. And this homomorphism accounts in the sense of other semirings, for instance, the tropical semiring, where you have the mean as addition and the plus as multiplication. I don't think this has been looked at and would certainly be interesting and worth investigating. I will stop with this, and I thank you for your attention, and I'm happy to take questions.